Welcome, everyone. We're here for Ben Gammage's second talk, Introduction to Wrapped Fukaya Categories. The first part of this talk is on the field's website. It's nicely edited. Okay, so
hopefully they removed all of my mistakes.
Yeah, that's right. There were mistakes remaining. So please interrupt with questions, and thanks again for agreeing to do this.
Sure. Well, thank you all for coming here 2 weeks in a row. I'm heartened that not everyone. Sometimes you give a two-part series, and the second time it's just the person who asked you and no one else. So sometimes even that is like too much to hope for, and it's an empty room. So thank you for continuing to come. I know that last week's talk was maybe not so exciting for the first hour. It was like a bunch of kind of stuff about Liouville, build up to like definitions in Liouville geometry, Liouville sectors, whatever. So this talk will be exciting, hopefully. I haven't actually planned that many sort of particular things to say in this talk, so this is really just going to be more of a kind of conversation, open-ended, let people ask questions and tell me where to go. But I'll sort of as a starting point for our conversation, I'm going to expand on the stuff that I ended with last time. So there's all kinds of structural results about the wrapped Fukaya category, and I'm going to kind of like spit all of those out in this part of the talk. And then after I've sort of said all of those, then we can discuss where we want to go and what kinds of computations we can do from those. Okay, so again, this is an introduction to wrapped Fukaya categories. Following Ganatra, Hardin, Shenda, 2, the second paper in the series, which is called no, that's the first one, which is called descent code, something about descent for Liouville sectors. Liouville sectorial descent, maybe. Yeah, and it has all kinds of a wealth of structural results about wrapped Fukaya categories. If I have some time, I'll say some things about, in fact, I certainly will have time. So I'll say some things about the third paper in the series as well, which explains how to understand these categories in terms of constructible sheaves. So the starting point for the talk is a Liouville sector. So, okay, so the reason why I spent all of last time doing all this kind of like maybe slightly boring stuff about like Liouville sectors and everything is so that this time I can just jump right in. So the starting point is I have M is so this is a Liouville sector, which means that, one way I can think about the construction of a Liouville sector is I can think of M as either a Liouville domain or a Liouville manifold, and lambda is a Legendrian inside. If I think of M as a Liouville manifold has an asymptotic boundary at infinity. Maybe I didn't introduce this notation last time. But if M is a Liouville manifold, then like it's the conicalization of it, it's cylindricalization of a Liouville sector. So the sort of boundary at infinity of the Liouville manifold is the sort of like actual boundary of the Liouville sector, or equivalently, it's the kind of projectivization of the infinite boundary of the Liouville manifold. So a Liouville sector for us consisted of this kind of data. It was the data of a Liouville manifold M together with a Legendrian at infinity. And the Legendrian could be empty, in which case you just have a Liouville manifold. So in last week's talk, I sort of indicated that given a Liouville sector, these guys described a construction of some kind of category, which is the wrapped Fukaya category associated to that Liouville sector. And so this is the category that we are going to be exploring today. Right, this is supposed to be a W for wrapped. Yes. And a tool which I find very helpful, which I sort of introduced briefly last time, but we'll go into more detail about now, is the skeleton of a Liouville sector is the set of points which do not go to infinity under Liouville flow. So what this means is that inside the Liouville manifold M, I can ask for the stable set for the Liouville flow, all the points that don't go to the boundary of the Liouville domain. And now I'm also including in the skeleton any point that goes to my Legendrian lambda. Because remember, I'm thinking of a Liouville sector as like I put lambda, I put this Legendrian inside the contact boundary of M, and then I complete M everywhere outside a neighborhood of the Liouville sector. Again, the kind of example, I mean, this infinity inside the Liouville sector you should think of as like, you know, the contact boundary of M minus the Legendrian lambda, basically. So the example is like if my Liouville sector is like lambda equals a 2-disk with 3 points in the boundary. So here's my 2-disk. Here is lambda. Then my skeleton is going to be sort of, this is my skeleton. So the idea is maybe, you know, if I draw this a little bit like I drew it last time, sort of. Here is my Legendrian inside of the boundary of the disk. This is my sort of 3 stops. And when I turn this disk into a Liouville sector, what that means is that I'm modifying my Liouville vector field, which inside the disk usually is just the radial vector field. I'm modifying it near here so that near here he sort of looks like he's going like out from this guy like this. So that means that like I'm going to infinity everywhere unless I'm exactly in these lines going out to the orange thing. Okay, and there's no kind of, in this case for a disk has no interesting topology, so there's no kind of compact part of the skeleton besides this point here. The skeleton is actually strictly isotropic, whereas sort of in a general Liouville manifold, usually you're going to have a Lagrangian skeleton, even of the compact part. And maybe another example is like M lambda equals T star S1. And I'll say maybe the boundary, the cosphere bundle of a point in S1. So when I write cosphere bundle over P, what I mean is like the projectivized, maybe I'll write it like this. The boundary at infinity of the cotangent fiber of S1 at some point P. Or in other words, the projectivized cotangent fiber. So here's my T star S1. I have some point P here, P. It's cotangent fiber at infinity, has these 2 points in it. And then the skeleton is the 0 section of T star S1. That's the compact part of the skeleton, together with that whole cotangent fiber over P. So I'll say this again towards the end of my talk, but what you should think of the skeleton as giving you, like roughly speaking, maybe this is not, you know, a theorem in the best generality, but like you should think of a skeleton as like, I mean, slogans, maybe. Okay. So slogans, 1, M is the cotangent bundle of its skeleton. So this is not literally true unless M is smooth. So this is literally true if the skeleton of M is smooth. So if the skeleton is smooth, like in this T star S1 case, the skeleton of T star S1 is literally an S1, and T star S1 is the cotangent bundle of that. Maybe the third example I should have written down here. I'll just do it up here. Example I could take the M is just the pair of pants, the 3-punctured sphere. And then actually, let me do 2 possible skeleton for it. So one possible skeleton for it is what people sometimes call the underwear of the pair of pants. So it's sort of this trivalent graph with 2 vertices like this and 3 edges connecting them on the front and back. And there's another possible skeleton you could have chosen, which has like which is still trivalent, but now it has sort of like 2 edges connecting these 2 vertices to themselves and 1 vertex connecting it here. So these are sort of obtained by a choice of homotopy of Liouville structures. The idea is that one Liouville structure is like everything is kind of going out like this on both sides, and in this Liouville structure you have like the Liouville vector field is going up like this on both sides and out like this from here. So there's multiple possible skeleta you can have. And so you can see that this manifold is not a cotangent bundle, but you should think of like if it were a cotangent bundle, it would be like the cotangent bundle of this singular thing, whatever that means. So that's the first slogan about skeleta. Any questions about this? Yeah, so that was going to be my second slogan, is that like you should think of like covers, open cover of the skeleton of M, or the skeleton of M lambda, is roughly speaking should be the same as a Liouville sectorial cover of M lambda. Again, I mean, I think, this is not theorem partially because, skeleta can have all kinds of like crazy behavior, but if you kind of like, for nice skeleta, this is going to be true. That like, so there's this work of Nadler, Eliashberg, Alvarez Gavela, I think those are the main names, called the sort of arborealization program, where they give a list, David Nadler gave a list of sort of model singularities in every dimension. Like in every dimension, there's some finite list of like singularities that you can reduce to. And so those guys showed that you can actually reduce a general skeleton of a Weinstein manifold to like that list of singularities. So in dimension 1, you can reduce to trivalent vertices, right? Like if you had a 4-valent vertex somewhere in your skeleton, you could sort of do a homotopy of Liouville structures to make it look something like this, for instance. And for each of these model situations, certainly we have nice local models of neighborhoods.
Does the category depend on this homotopy of Liouville structures?
The category is insensitive to it. Yeah, I mean, the space of like if you have a Stein manifold, like I mean, the space of Kähler potentials for a given Kähler form is, I think, convex. So it's in particular contractible. So it's not going to, the category is not going to depend on it.
And the fact that the category doesn't depend on it, is that, does that involve these continuation maps, or is it a different?
This is maybe a different fact. The continuation maps are about kind of the wrapping, about Hamiltonian perturbation. It might be related. Let me not try and, let me just say that the category as constructed is like not sensitive to precisely what the Liouville form is. I'll get to the category in a moment. Yeah. So let me do this example here. So in this example, the point is that like, the point is that like, when I have this picture here of like, I have this Liouville manifold, which is the pair of pants, and I have this skeleton on it, this is telling me that I want to glue this together, is glued from 2 copies of this manifold here, this Liouville sector here, which is the disk, which has skeleton given by a trivalent vertex. So you can see that there's like a trivalent vertex on the front and a trivalent vertex on the back, and it's glued together along 3 copies of the disk with 2 mark points on the boundary. So this is the basic thing, is that like drawing the skeleton is for me like just a helpful combinatorial way. If you have if you know the sort of combinatorial type of your singularities of the skeleton, then it's telling you like local models for those. Like in this case, it's literally just like this, and it's just telling you how to glue this thing together from these kind of local models. And so later we'll see that the theorem is that the category is a sheaf, actually co-sheaf on this thing, which means like if your manifold is glued together from pieces like this, then your category is glued together from pieces like this. So Liouville sectors are the appropriate notion of like open sets for covering a Weinstein or Liouville manifold or a Liouville sector. Okay, so that's what the Liouville sector and that's what the skeleton is. So that's the role that it's going to play in this talk. Any other questions?
Question about language for sector. If you glue together Liouville sectors, are they always still Liouville sectors?
Yeah, I think I think so. I mean, there's some, maybe I'm hesitating just because like, the product of Liouville sectors, as I've set things up, technically the product of Liouville sectors is not itself a Liouville sector. It's like a cornered Liouville sector because there's like a codimension 2 component to it, but like you can smooth the corner. So like it's really equivalent to the thing before. And basically what I'm saying is, roughly speaking, the answer is yes. Of course, it might be that your Liouville sector, when you glue them together, you get a Liouville manifold, a Liouville sector with empty stop in the boundary, which is fine. I mean, that's often what you want, is that like this guy is a Liouville manifold, like a Liouville sector with no stop at the boundary, but I've glued him together from 2 things that are Liouville sectors. Of course, I could also have been interested in a Liouville manifold that did have a stop at the boundary, so I could equally have been interested in something that like had a stop here and a stop here, and then so he has these extra, pieces of non-compact skeleton coming out of it. And again, maybe this was a building block in some more complicated thing, like maybe I wanted to glue this to some other, pair of pants over here or something, whatever. And that can often be the case. Okay, I'm now going to spend the rest of this talk telling you structural properties of the wrapped Fukaya category. Facts about wrapped Fukaya category. I'm doing better at saying about because I say it a lot in class. So I'm only here 2 months and already I'm adjusting. Although I still say Z instead of Z, so that's going to take me some more time. Okay. So the first one, it is generated by co-cores and linking disks. So again, I didn't give a precise definition last time of what these are, but I'll just sort of illustrate by picture. Like a linking disk is like a disk that links the stop. So here's the stop at infinity is this Legendrian, and there's a little disk in the symplectic manifold that links it. So this stop has a linking sphere inside of the contact boundary, and that sphere is filled in by a linking disk. So I'll draw these kind of these are the co-cores and linking disks here. So this guy has a linking disk, and then the co-core is like sort of like the version of a linking disk for a piece of the compact part of the skeleton. So like locally, it looks like a cotangent fiber. So like here's an example of a co-core to this part of the skeleton. So again, in this picture, kind of my linking disk like this. Here's my linking disk, and then I also have a co-core, which is this cotangent fiber here. So those objects generate the wrapped Fukaya category. And roughly speaking, the slogan here is that you should think that Hom from one of these objects is sort of measuring, maybe a slogan, Hom from one of these objects, the linking disk at P. So this is a functional, so this is a Hom in the wrapped Fukaya category of M lambda. And this is like dP, maybe this is my point P here, I mean, this is the like component of my Legendrian that this thing is linking, and dP is sort of measuring, so this is a functional in my category. I take as input an object of my category, and it spits out a vector space or chain complex or whatever, and this measures, roughly speaking, the stock, or the really micro-local stock, or measures like the behavior of my Lagrangian near P. So I'm being imprecise about this, but the idea is that like if I have an object of my Fukaya category, it's a Lagrangian in this symplectic manifold, and like I can ask, does my Lagrangian, after wrapping, like go asymptotically to P or not? And like, so for instance, if I had a compact Lagrangian, then Hom from dP to him would be 0 because my Lagrangian doesn't see P. Or I guess I guess it depends on my convention for like which way the wrapping goes, but Hom from dP to like one of these two guys is going to be non-zero and one is going to be 0, and that has to do with the fact that like one of these guys after wrapping goes toward P and the other one doesn't. So that's what's happening. Later on, when I describe my Fukaya category as a category of sheaves, this will be the functor that measures the microlocal stock at my sheaf near that point at infinity. Or if it's a co-core, then it's actually measuring the stock of my sheaf at that point that it's a cotangent fiber too. So I'll say those things a little bit later. So let me kind of do this example here. So this Fukaya category, the Fukaya category of this Liouville sector, the disk stopped at 3 points, is generated by 3 objects, D1, D2, and D3. And again, depending on my conventions, but basically what we're going to see is that D1 is that I have like one Hom from D1 to D2. That is, the Hom from D1 to D2 is a one-dimensional vector space. And that has to do with the fact that like, okay, these two objects right now don't touch each other, but after I wrap D1, he will touch D2. So I get a map from D1 to D2. Similarly, I get a map from D2 to D3. And I actually also get a map from D3 to D1. But after those 3 wrappings, if I wrap all 3 of these guys, maybe I'll kind of draw a picture of what it would look like if I had done all 3 of these wrappings, so that now this guy is going to here, this guy's going to here, and this guy's going to here. Then I would see that I get this holomorphic disk in the middle, which is a mu3, and what that's going to tell me is that these 3 guys form an exact triangle. So in the sense of this Fukaya category is a triangulated category. Actually, maybe, I mean, after I take its appropriate triangulated envelope, really it's a stable infinity category, whatever. It's a triangulated category, it has a notion of exact triangles in it, and these 3 guys form an exact triangle. There's maybe a better way to say that. I know I said this in terms of this holomorphic disk, and I wanted to get away from that in this talk. So I'll say a different way to understand that in 1 second. But first, let me tell you the sort of consequence of this, which is it's that the wrapped Fukaya category, in this case, of the disk with this 3 marked points, is isomorphic to representations of the A2 quiver that is the quiver with two vertices and one edge between them, which, right, an object of this category is a pair of vector spaces V and W with a map between them. The idea being that kind of since three of these objects are in an exact triangle, knowing the third object is redundant because it's the cone on the first two. So, another way to say what this category is it's like the universal exact triangle category. So I can think of this as like V, vector spaces V and W with a map between them, and then a third vector space, which is the cone on that map F. And this is an exact triangle. So the point I'm trying to make is that, like, you can break this symmetry. Like this guy has a nice sort of Z mod 3 symmetry, but you can break it and say that, like, actually, even though I said this was generated by linking disks, I didn't need all three linking disks. Two linking disks were enough to generate the category. And those two linking disks are D1 and D2, and there's one hom between them and no hom the other direction. So that tells you that the category is equivalent to the data of a vector space, another vector space, and a map between them.
Can you say a little bit about whether these vector spaces are finite dimensional, graded?
Yeah, so well, okay, so I didn't talk about grading data yet. There is a way to grade this so that this is just category of vector spaces with a map between them, and then really I mean, the thing that is easiest for me to say is that, like, what I like to do is I like to you shouldn't impose finite dimensionality constraints on the vector spaces. What you should do is first describe the category where the vector spaces are possibly infinite dimensional, and then take compact objects in there. And the point is that in this case, that does impose finite dimensionality because compact objects in this category are precisely the finite dimensional vector spaces. So this category is, in this case, just the data of two finite dimensional vector spaces with a map between them. Or the derived category of that. I'm, I guess, taking the derived category of that. Sorry, I know I'm being a bit imprecise about whether I'm working with like some actual, I mean, usually whenever someone says wrapped Fukaya category, I mean, whenever I say wrapped Fukaya category in this talk, let me put it this way, I'm always like passing to the like, pre-triangulated envelope of twisted complexes or something, which means like working in a setting where I'm in a derived category, basically. I mean, then you can ask a question, like which objects are represented by actual geometric Lagrangians, and that can be a maybe slightly more difficult question. Like I'm formally enlarging, I'm starting with the category with actual Lagrangians and enlarging it by like, allowing myself to take twisted complexes of those. But actually, those things are still geometric. So let me say one more thing about this exact triangle calculation, since I sort of fudged it before by drawing a picture of a holomorphic disk. I mean, that's a perfectly good computation, but I'd like to give a different explanation, which is that if I have two Lagrangians, this is a sort of separate fact. If I have two Lagrangians in the wrapped Fukaya category, L1 and L2, and so I see that I have a point P is so if I have P is an intersection point of L1, L2, so I can think of this as a point in the hom from L1 to L2. Right, I told you that whatever homs from L1 to L2 like have a basis given by intersection points. Maybe after applying this wrapping Hamiltonian, I can ask, what is the cone on this map P? Like, in other words, I can form the two-term complex. If I'm thinking of like, if I'm in some category of twisted complexes or something, then I can form the two-term complex given by like these two objects and the map between them. Or I can take the mapping cone, however you like. And I can ask like, okay, this is an object in the sort of like derived category or twisted complex category of whatever I'm doing. Like, what does this correspond to geometrically? And the answer is that the cone on an intersection point in the Fukaya category corresponds to doing a Lagrangian surgery on that point. So what that means is that this is what I would get by sort of doing this Lagrangian surgery of L1 and L2 on this point. This is some, important geometric fact about the Fukaya category, which I won't try and justify. And so in this example I did, where I had these linking disks here. So I said that okay, so I computed the Hom from D1 to D2. I computed the Hom from D1 to D2 by saying, okay, I start by wrapping D1. So I take this guy and I apply the sort of wrapping Hamiltonian to it till he crosses and hits D2. And then he has an intersection point. And now I can ask, what's the cone on that intersection point? P. And I take the cone on P. And what am I going to get? Now I'm going to get, this Lagrangian surgery here, where I have this guy and I have this guy. And this guy wraps off of himself. So he ends up, you can imagine the Liouville flow just kind of pushes him off to infinity since he's not wrapping any stop. So this guy is a zero object in the category. So what I find, and this guy, on the other hand, is clearly the same thing as my D3. He's a linking disk to this third stop here. What? I call what? The cone, well, the cone is the surgery. It's the surgery on these two Lagrangians. So it's a new Lagrangian which now may have multiple components. I mean, my original Lagrangian also may have had multiple components, but I might, I should really allow immersed Lagrangians. I mean, I said that my category was smooth Lagrangians, but really I should have already at the very beginning allowed myself immersed Lagrangians, maybe. And so I can think of this as think of this L1, union L2 itself as being some immersed Lagrangian, and this is a Hom from it to itself, and then this is the cone on that or something. Yeah.
Should there be any constraint on the integral map when we take the
On the degree?
Yeah.
Yeah, I'm trying to avoid dealing with grading issues right now. So, I mean, maybe yes, but let me, I mean, also, another question you could have asked me is how did I know to do this surgery where I went this way instead of the other one where I went the other way? Let me kind of not worry about those questions right now. I mean, and also, you can treat P as a map from L1 to L2 in the picture I drew, or as a map from L2 to L1. And, there's various, it depends on what the gradings were on these Lagrangians, et cetera. But this is at least a heuristic that you should, that should be a way of understanding why these three guys form an exact triangle, right? So a cone is just my, my way of referring to it. If you don't like, stable infinity categories, cone is a way of referring to the third member in an exact triangle. So if I have a map from D1 to D2, then the third guy that fills in that triangle is the cone on this map. And so what I'm saying is that kind of another way of saying this cone thing is just that L1, L2, and the surgery of L1 and L2 fit into an exact triangle in the Fukaya category. Okay, so this was some calculation of the wrapped Fukaya category of the partially wrapped Fukaya category of the disk with three stops on the boundary. So more generally, the wrapped Fukaya category of this is the two disk with lambda equals n points on the boundary. Is equivalent to representations of the the A n minus one quiver. So an object in this category is given by the data of n-1 vector spaces, which are the vector spaces given by Hom out of like these n-1 linking disks. And then the final linking disk can be obtained as a sort of like twisted complex of the other ones by continually doing Lagrangian surgeries until you have just something that looks like this. So that was my first fact. Whoops. That was my first fact I told you about the wrapped Fukaya category, is that I told you a set of generators for it. So now, like, at a minimum, if someone tells you a Liouville manifold and they write down the skeleton, then you can write down some set of objects and you can say, okay, I know these objects generate the wrapped Fukaya category. Now I just need to compute their Homs or something. But already, knowing some set of generators, knowing some basic facts about cones between them can be like really useful. Okay, so my second fact is the title of this Ganatra-Pardon-Schende paper, which is again, sectorial descent or whatever it's called. I mean, the simplest thing to say is that if a Liouville sector, if a Liouville manifold or Liouville sector can be written as a cover of others, let me just do the simplest case where it's a cover of two pieces, like say M1 lambda 1 union M2 lambda 2 along the intersection of some like M prime lambda prime, then, as I said, the wrapped Fukaya category of M lambda is the push out of the wrapped Fukaya categories of these things. It's obtained by gluing together this category and this category along this category. And more generally, if you had a like larger cover with multiple intersections, then you need to do something. You need to take a bigger thing. And so the general statement is that, i.e., this functor of taking the wrapped Fukaya category. So first of all, in the first Ganatra-Pardon-Schende paper, they proved this is functorial for inclusions of Liouville sectors. That if this Liouville sector includes into this one, then there's a functor from the wrapped Fukaya category of this to the wrapped Fukaya category of this. And then in the second one, they proved that this is a co-sheaf. For covers by Liouville sectors. Again, I think sheaves are more familiar to people than co-sheaves. But a co-sheaf is just a sheaf with the functoriality reversed. Or there's another trick that you can use, which is that if you pass to this ind category, like I said, if you don't, the reason why I like to start by not imposing any finiteness conditions on my vector spaces is that if you work with, if you allow all of your vector spaces always to be possibly infinite dimensional, then you can always pass to the right adjoints of these functors, and that changes all the directions of your arrows, and so you get a sheaf of categories rather than a co-sheaf. So note, if I take the ind version of the wrapped Fukaya category, which means like, I'll just say like allow possibly infinite dimensional vector spaces, this can equally be understood as a sheaf of categories by taking right adjoints. Again, when I write this kind of like union here, what I mean is kind of a push out where kind of this thing has functors to both of these guys, and I kind of like fill in the bottom corner of the square. If I reverse those arrows, then I could think of it as a pullback instead. And then I can think of a sheaf instead of a co-sheaf. So if you're willing to work with infinite dimensional vector spaces, then this statement is just that like, the Fukaya category can be constructed by, local calculations on a Liouville sectorial cover. So already at this point in the talk, now you know how to compute the wrapped Fukaya category of a punctured Riemann surface.
Near union diagram.
Yeah.
Your push-out diagram.
Yeah.
You have functors from the small to the two sides.
Yeah.
Those functors, what are they?
Right. Basically, so if I have a Liouville sectorial inclusion, so maybe suppose I
Is it somehow clear that the generators get sent to things that you can identify?
yeah, I mean, let me try and, so suppose I had this guy, the disk with 4 mark points, which last talk we decomposed as a disk with 3 mark points, a disk with 3 mark points, and a disk along a disk with 2 mark points here. Then you can see that kind of this this guy here, I have a generator here in this disk with 2 mark points, which is this co-core, and he sort of just is going to this co-core in here, and this co-core in here, or linking disk in here. Yeah, linking disk. I guess these are all linking disks. I mean, this guy is actually a linking disk too, even though, whatever. To me, these are, I tend to use these words sort of synonymously because ultimately in the proof of these some of these Ganachar-Barton-Schende theorems, they like to embed their Weinstein manifold. Like you take your manifold or sector that you're considering, and then you put it at infinity as the part at infinity in a larger sector, and then all the co-cores just become linking disks. I'm just saying, you could imagine taking the whole skeleton you cared about and putting it at infinity as a stop in something 1 dimension higher. And then all your co-cores become linking disks. Anyway, let me not worry about that. So the point is that yeah, it should be clear that this linking disk is still a linking disk over here, only now he's doing some more, there's some more interesting behavior to his wrapping. Here, the wrapping just kind of stopped here and here. He is not really doing anything. But here, well, I guess it's not that much more interesting, but whatever.
Is there some kind of injectivity of these functors or is it not possible to formulate that?
I don't think so. I don't think you can guarantee that.
Like some kind of faithfulness.
No, I mean, for instance, I could take the disk with 1 mark point on the boundary. So this guy has, anytime you, this guy has 0 wrapped Fukaya category, which you can kind of tell because he's generated by this linking disk, but this linking disk can kind of wrap, so he comes, he can just wrap around here, and then he comes, and then he becomes something like this. And so basically this Fukaya category is 0. You can also tell this from the skeleton, that anything that has a skeleton with boundary has got to be 0 because well, if ultimately we're going to think about microlocal sheaves on the skeleton, and a microlocal sheaf can never have singular support that just kind of ends somewhere. Anyway, this guy has a wrapped Fukaya category of 0, but he has a subsector, which is the disk with 2 mark points. This guy embeds inside of here as a subsector, but the functor is actually 0. So there's no kind of guaranteed faithfulness or anything of these functors. Homotopy push out, yes. Yeah, so you have to be maybe, yeah. And again, if you work with infinite dimensional vector spaces, you can think of it as a homotopy pullback instead. So the punchline here was that now from these two facts already, you know how to compute the wrapped Fukaya category of any punctured Riemann surface. Your recipe is going to be like, 1, find a skeleton, which a skeleton of a punctured Riemann surface is basically the same data as a ribbon graph. Right? It's like it's like combinatorial. It's like a combinatorial kind of thing, a graph that's drawn on the Riemann surface with a cyclic order at each vertex, so that the Riemann surface deformation retracts onto it. A ribbon graph is like a graph that has a little bit of a ribbon, and the little bit of a ribbon is like a little like Weinstein neighborhood, like a sort of cotangent neighborhood of this singular skeleton thing. So you find a skeleton, and maybe in fact you find a skeleton, and then step 2 is like glue together local categories. So what I mean by that is that locally, this locally looks like an n-valent vertex, whatever. The skeleton of a punctured Riemann surface, you can always make it so like locally it looks like one of these kind of n-valent vertices. In fact, you can always break this up so it just becomes trivalent vertices if you like. And I told you what the wrapped Fukaya category of this thing was, and then you just need to glue these together. Well, yes and no. I mean, it depends what kind of answer you want. So maybe like an example, I'll give 2 examples. I mean, I gave one of these last time. Let me start with this skeleton of the pair of pants. This sort of like underwear type skeleton. And one way to understand what this category is wrapped Fukaya category equals. So I told you that the wrapped Fukaya category of like one of these, so this guy is glued together from 2 trivalent disks. And I told you that one disk with a trivalent with 3 stops on it was equivalent to the data of an exact triangle of vector spaces, like U, V, W, exact triangle. And the other one is also an exact triangle. And then they're glued together along these things, which the disk with 2 points is just the category of vector spaces. So if you take that like homotopy pullback, it's telling you to just take 2 exact triangles like U1, V1, W1, and U2, V2, W2, where since this guy is on the back, his maps are going in the opposite direction. And then you identify them along by gluing along the U1, U2, these vector spaces. So that's the same thing as saying that like it's the data of vector spaces, of 3 vector spaces with like 2 exact triangles running among them. Like one exact triangle going one direction, one exact triangle going the other direction. So that's just the obvious, what you would try and do if you were just like literally just gluing these guys together in that way. Of course, now you can be like, well, okay, this gives me some description of the category, like, via this homotopy pullback, and like, but, is this that explicit or something? And then what, you might actually instead want to try and like figure out in this description, what are the generators of the category? Like, I have these 3 cocores, and you can try and figure out what these are in this terms and then calculate Homs among them. Or there might be some better generators. It turns out that maybe some better generators are actually like the compact Lagrangians. This category turns out to be generated. Is that right? No, that's not right. No, that's not right. Yeah, you can figure out what these 3 cocores are anyway. And it's going to turn out that this description, sort of, if you think hard about it, I guess I actually wrote a paper about this. This was my first paper in graduate school with my advisor. We did this in higher dimensions too. And you can check that, like, combinatorially, there's a way to check that, in this case, this agrees with the category of matrix factorizations on C3 for the function xyz. And again, you can do that by figuring out exactly, like inside of here, what objects these cocores correspond to, and then sort of like carefully checking against Homs in this category, which also have some algebraic description. Maybe a better, example, like a better calculation, or at least a more easy to understand one, is the one which I sketched last time, where
So just 1 second, Ben. So I'm tempted to ask you to do these in detail, but I don't know what else you have planned.
yeah, I would say this calculation is not helpful to do in detail. Let me say a little bit about this calculation.
Okay.
It's a little bit better.
If you have the time to do it, you know,
Yeah,
go through it, like, don't make it just a side remark.
yes,
It could be,
yeah. I mean, I don't know. Let me not try and do this calculation right now. I feel like I might fumble it anyway. I mean, this one is a little bit easier. So in this one, kind of, once again, I'm this, if I have this skeleton, it's telling me a Liouville sectorial gluing, I'll just write the skeletons down. So like this is a copy of T star S1 with 1 stop. Maybe I'll draw the gluing like this. So I have a copy of T star S1 with 1 stop.
choosing a skeleton.
Yeah, I started by choosing a skeleton.
Now you're decomposing it into.
And now I've taken an open cover of this skeleton. So this skeleton has an open cover by, like, you know, this circle together with a little piece coming out of it, this circle with a little piece, and this, the intersection is that thing there. And that is a combinatorial way of telling me that this pair of pants is glued together from a cylinder with 1 stop, a cylinder with 1 stop, and a disc with 2 stops. And these categories I sort of calculated last time. Let me just so this is this is one of these categories. Actually, it's either of these categories here. And so I said that this category is generated by 2 objects, namely the linking disk to this stop, together with the co-core to the compact part of the skeleton. In fact, you only need the co-core to the compact part of the skeleton. It turns out that that's enough, because sort of he has a natural hom with himself, and if you take cone of that, then you sort of like peel off the bottom bit, and you just end up with the co-core here. So it's enough to just take this co-core.
But it should be equally easy to just take the generators you told us to take.
You could take both, yes. Let me just start by taking this one here. And what I'm going to find basically is that let me call this guy L. What I'm going to find is that the hom from L to L is going to be, well, I'll just say what it is. He's going to be well, actually, as a ring, he's going to be isomorphic to the polynomial ring in 1 variable, k adjoint x. And the reason for this is, roughly speaking, that up here, there's a stop, so he's not going to kind of do anything interesting up here, because if you tried to wrap him up here, he's going to run into the stop. But down here, he can wrap himself infinitely many times. So if I didn't have this stop, I would get the polynomial ring in 1 variable and its inverse, coming from the fact that I have like all of my x to the n's here and all of my like x inverse x to the minus n's up here. But here I just have 1 variable. And it's going to turn out, again, as I said, that if I take the cone on this map L to L, then that is going to fit into an exact triangle with my linking disk D.
So then this fact that you just wrote here is because you're like taking a intersection of L itself and doing a surgery, and you get.
Exactly. So if I wrap L once on the bottom and then take the surgery on that, then I get like some piece on the bottom which kind of goes away, and I'm left with like some piece L has like wrapped around now once up here and sort of done something like this.
Okay.
I mean, I can try and draw it, but I'm not good at doing these kind of drawings. But I take L, oops. Let's see if I can try and draw it. I have L, and then I have the like once wrapping of L on the bottom, and I take this the cone on this thing, and what I end up with is sorry, I've wrapped L around once. Okay, maybe I'm not going to try and draw it. I'll let people do it in their imagination. But if you wrap L around once and then take the cone, then you split off a piece on the bottom and this thing up here. I'll do a more in-depth version of this calculation in a minute.
What is on the bottom? Go away. Because
The thing on the top is going to link the stop here.
the stuff is on one side, but the other side of it is nothing.
So if I wrap once, the point is that after wrapping once, I'm going to get something that like my L is going to be like, he's going to be something like this. Let me see if I can do this. I have my L and I have my like once wrapped version of L. So then the point is that like when I do this surgery, now I get something like this and like this. The thing on the bottom is not wrapping anything. So he's a zero object in the category, whereas this thing that is on the top is wrapping a stop. So it's going to turn out that the wrapped Fukaya category of this thing, of the wrapped Fukaya category of this guy, is just going to be modules over k adjoint x. So I told you that that this guy generates and that his HOM is just k adjoint x. So that tells you this category is just modules over k adjoint x. And this equivalence sends this Lagrangian L to the free rank 1 module over k adjoint x, and it sends the linking disk D. Well, it's something that has a two-term resolution by copies of the ring k adjoint x with the map x here. So that's the module k, or k adjoint x mod x. And once you know this, then of course you can convince yourself of that the endomorphisms of L is going to be it's going to have a two. It's going to be like, well, if you were careful about gradings, it would be k in degree 1 plus k. Sorry, the endomorphisms of D is going to be like k in degree 1 plus k in degree 0, coming from the endomorphisms of this thing in here. The x of this module has a k adjoint x module. Yeah.
I think but if your Lagrangian doesn't intersect the skeleton, it has to be 0.
If not exactly, well, yeah, certainly if you have a basically like if you have if you have a disk at infinity like this that doesn't wrap the stop, then it can just be pushed off of itself, so it's going to be 0.
That's like a special case. There's not.
I mean,
Can it just flow it along the?
yeah, I mean, the point is the Liouville vector field just kind of like, I mean, yeah. I guess, well, the point is that, I mean, I guess I'm only considering exact Lagrangians. So maybe that's true. I mean, if you were allowed non-exact Lagrangians, you could imagine like this circle right here, which doesn't touch the skeleton, but should still be like a non-trivial object in the Fukaya category, ultimately. I mean, he will flow down, but he's equivalent to like if I sort of flow him backwards by Liouville flow, he'll flow back to something here. Yeah.
Is it obvious that like any module over K is just a reiterated cone of L?
That's this. Okay, this is a this is a fact about algebra you're asking about. Are you asking about the fact that like k adjoint x generates the category of modules over k adjoint x, or?
I mean, we also consider direct sums.
Yeah, I allowed direct sums and direct sum ends. Yeah. So what this what this, calculation tells you is that the wrapped Fukaya category of the pair of pants is going to be equivalent to the data of, M, a K-adjoint X module. So that's an object in this category here. N, a K-adjoint Y module. I'm just taking the pullback of these maps of categories here. So I have a K-adjoint X module, I have a K-adjoint Y module, and then the restriction from from this category to this category is like, well, okay, I'm just restricting to what my module is doing up here, but I said that this linking disk is measuring like what this thing is. So this is, M a K-adjoint X module, N a K-adjoint Y module, plus an isomorphism of M mod X, maybe I should say like M tensor over K adjoint X with K adjoint X mod X is isomorphic to N tensored over K adjoint Y with K adjoint Y mod Y. And if I think harder about what this category is, this is actually, I'm taking this whatever pullback of categories, and if I think harder about what this is actually just the data of a module over K adjoint XY mod XY. There's some whatever analytic difficulties here where like really instead of, this is like the category of quasi-coherent sheaves on the variety, XY is equal to 0. Really, I should have had the category of incoherent sheaves, but let me not worry about that difficulty.
Could you explain again the relation there?
This let me explain it this way. Oops, I'm erasing my codescent thing, but I have the variety XY is equal to 0. So this is like this variety. It's like two copies of the complex plane meeting together at a point. And maybe I have a closed cover of this thing. XY equals 0 is equal to like the X plane, the X complex line here, the Y complex line, and they're glued together along one point, namely the origin, 0. And there's some theorem that coherent sheaves satisfies descent along proper maps. So actually, it turns out that coherent sheaves on XY is equal to 0 is obtained as like coherent sheaves on the X copy of C, coherent sheaves on the Y copy of C, glued together along coherent sheaves on the point 0. So this is like some, algebraic fact that like, a module over K adjoint X and a module over K adjoint Y, which agree at 0, is the same data as a module over like the gluing of these spaces like this. So this is kind of like I've taken my sort of abstract categorical gluing here and I've like translated it into algebraic geometry, and that lets me do a kind of an easy realization of like what this category is.
Right. So if you have two linking disks.
Yeah.
By this gluing thing, they make a Lagrangian circle, which is trivial or something like that.
You mean these two linking disks?
Yeah.
You mean that like I have a HOM from this linking disk to this linking disk together up here? Is that what you're asking?
The linking disks in the cylinder.
These are co-cores. Oh, in these. Oh, you mean this linking disk in here?
So when you glue them, they make a Lagrangian circle, compact Lagrangian. Which is trivial.
Sorry, when I glue what?
So the reason that we take XY to be 0. So I thought it like as the fact that if you have two linking disks.
No, I know, but no, because X and Y are the map. X is the map, like in this picture, in this cylinder with this stop here. X is the map from this Lagrangian to itself, where he's like wrapping himself back around here. And similarly, like so this Lagrangian has a map where he does something over here, and similarly this Lagrangian has a map where he does something over here, and that's Y. Yes, I guess the point is that like if you do both X and Y, then basically this has to do with the fact that like these two guys are kind of not talking to each other, X and Y. I don't know, you can think harder about this, but anyway, this is a calculation, and it's a calculation of this guy here. So I had one other calculation I wanted to do, but I don't know if you wanted to take a break or.
No, let's go ahead.
Okay. So I was telling you facts about the wrapped Fukaya category. I told you 2 facts so far. And those facts we found out were already like really, really useful, right? The first fact was I told you a set of generators. And the second fact I told you was that the wrapped Fukaya category satisfies the descent or codescent for covers of Liouville sectors. And so there's one more fact that I wanted to say, and I said this at the end last time, so I'll just repeat it now. So fact 3, it's that removing a stop corresponds categorically to quotient of the wrapped Fukaya category by the linking disk to the stop. So maybe an example. So I could take this disk with 3, well, I could take this disk with 3 mark points here on the boundary, and then I can remove a stop. So I like delete this stop here from my Liouville sector, and I keep only this smaller, this smaller Legendrian, which just has these 2 points. And so previously my category was generated by these 3 linking disks, and now kind of this linking disk becomes 0. In fact, maybe I should say, you know, that sorry, before I do this example, let me do something else. I'm going to erase this over here. Before I do this example, I want to explain why this should be true, which is that like here's the boundary of M. Here's my stop. And you know, I have, if I have a Lagrangian L, like here's a Lagrangian L, which is some Lagrangian in my category. And here's a Lagrangian L prime. And so like removing the stop identifies L and L prime. Right, L and L prime are like doing the same thing roughly in the compact part, and then in the non-compact part they differ, but they end up on opposite sides of the stop. And so what does it mean that removing the stop identifies L and L prime? It means that removing the stop does some localization to my category where I force that L becomes isomorphic to L prime, which means I force that the cone on some map between L and L prime becomes 0. And L and L prime fit into an exact triangle with this disk here. So the difference between L and L prime is this disk D. So precisely like removing the stop where I say like I'm allowing L to wrap past the stop is precisely saying I'm killing D, which D is like the difference between being on one side of the stop and being on the other side of the stop. So this says,
Slightly technical question.
Yeah.
So I understand what you just said, but
Yeah.
but it's at odds with the usual idea of localization, where you don't change the objects of the category, you just change the morphisms.
yeah, I mean, you sure, well,
What do you mean? What is meant when people say that an object becomes zero? What does that really mean?
well, it means that the identity morphism of the object becomes identified with the zero morphism.
But is that part of the theory of localizations of categories, that you can have objects that somehow
Sure. I mean, I don't know what your model of localization of categories is. What's your like favorite example of a localization of categories? Maybe I can try and
just
fit
like
into that
constructing
framework.
a derived category.
The construction of the derived category is where you declare certain objects to be quasi-isomorphic to each other, where they weren't before. Yeah, so, okay, so the point is that like here I have a map from L to L prime, or maybe from L prime to L, depending on what my conventions are. I mean, maybe you know, I could have drawn them like this or something, whatever, so I could see an obvious map between them. And I'm inverting this map. That's where the localization is. I'm formally adjoining an inverse to this map. But adjoining an inverse to this map is the same as like saying that the cone on this map is going to become zero in the localization. You know, even in your example of like, you know, the derived category, you invert quasi-inverses, quasi-isomorphisms, you know, you could have like, you know, like had a category where like formally you say like, I take, you know, I take a quasi-isomorphism between two things, and like, you know, inverting whatever is like killing the difference between those two things. So there are just two different ways of thinking about the same operation. So this localization is like formally adjoining an isomorphism there. And formally adjoining an isomorphism there is the same thing as saying that the identity map of this third object becomes identified with zero.
I see. So it's just exactly the same as if you had a vector space with the identity map to itself as a complex, and that is quasi-isomorphic to the zero complex. And so
yeah, that D would become a two-term complex like this, which is equivalent to the zero complex.
Yeah.
Yes, correct. Yeah, this localization of categories is sort of a remarkable operation, and it can behave in surprising ways sometimes. But that's what you're doing here. So you're doing this localization, which I like to think of as killing the linking disk. And again, killing the linking disk is exactly saying that like I'm identifying L and L prime here. But sort of killing the linking disk is the most I don't know, economical way to say that operation. So like in this thing, so what happens when I remove the stop? I'm killing this object. Kill this object. So categorically, what's happening, previously the data of this category, I said that the wrapped Fukaya category of this thing was equal to the data of an exact triangle. I guess I'm just almost literally going to repeat what I said before. The data of this category is equivalent to the data of like an exact triangle of guys A, B, and C. And then what I'm doing here when I remove the stop is I set C equal to 0. So kind of this is the same thing as like exact triangles A, B, 0, which if the third term in an exact triangle is 0, that's the same as saying that this map A to B had to be an isomorphism. So this is the same as just the category of vector spaces. So kind of up to a grading shift, possibly. I mean, again, I'm not being careful about gradings. I think that if I were, I would have a grading shift somewhere. But these two linking disks, you know, like clearly like look the same. You know, like after I remove this stop, like these two linking disks become identified. They were different objects in this category, but they become isomorphic objects in this category, which is just equivalent to the category of vector spaces now.
So if you have a disk with one stop.
What?
Like if you have a disk with one stop,
Yeah, well, a disk with one stop is going to be the zero category, but yeah.
If you glue that to one of these, the disk here, it's just like removing that stop. That is.
Yes. Yeah. Right. Okay. So that's actually an interesting point. I'd never thought of it that way. I mean, what you're saying is that like if I take this guy here and then I glue on here a disk with exactly one stop,
Then it's a special case of that.
and then yeah, I guess then the point is that like yeah, I guess then the point is that now whatever vector space I had placed here is forced to become zero because over here he has to be zero. So yes, that's another way you can think of it in terms of the second fact. Okay, so those are my three facts that I have about the wrapped Fukaya category. Those are kind of the most important three facts. And I have one more calculation that I'd like to do. So now I'm going to explain, I'd like to explain the main theorem, or at least part of it, of the third Ganatra-Pardon-Shenda paper, which is called Microlocal Morse Theory of Wrapped Fukaya Categories, which tells you that the wrapped Fukaya category is equivalent to a category of constructible sheaves if you're a cotangent bundle. Let me state part of the first, let me state the first step in that proof this way. So theorem, this is from Ganatra-Pardon-Shenda 3, microlocal Morse theory. So let M equal T star X and stratify X. So let M be a cotangent bundle to a manifold. Stratify X by a triangulation T. Okay, so take a triangulation of my manifold X, and that gives a stratification of X by the strata in the triangulation. And then I can take lambda to be the boundary at infinity of the union of conormals to strata. Strata in the triangulation T, whatever. Right, so you know, the example here is going to be like maybe X is like S1. In this case, maybe I triangulate S1. Here, I'll draw it like this. Maybe I triangulate S1 by it's a union of two simplices. Of this simplex and this simplex here. And then I take the union of conormals. So that gives me, in addition to this compact part, the like stops given by the conormals to this point and the conormals to the other point, right? Because the conormal to the open part is just the zero section. So I do that. Then the wrapped Fukaya category of M lambda is equal to functors from the exit path category of the triangulation of the stratification to vector spaces. Right, so the exit path category of a triangulation okay, I'll do this example here. In fact, maybe I'll just draw a triangle on the board. Maybe I'm in 2 dimensions now. Okay, if I have a 2-dimensional triangle, the exit path category is the category whose objects are, well, if your strata are all contractible, you just have one object for each stratum, and the morphisms, if your strata are all contractible and you have a nice stratification, this exit path category of the stratification is just the poset, is just the stratum poset. I mean, maybe I should just say this. I mean, this is equals stratum poset, right? So in this case, it's going to be it's this poset, right? Where this vertex corresponds to the big stratum, these vertices correspond to the 3 edges, and these vertices correspond to the 3 vertices. So it's called the exit path category of the stratification, because you're always allowed to exit a stratum into a bigger stratum, but you're never allowed to return from a bigger stratum into a smaller stratum. And so you can see it's just like it's like a barycentric subdivision post set of your original triangulation. But it's like, this is a super nice category, right? I mean, like, this is a post set. So I told you that the wrapped Fukaya category of this thing is functors from a post set to vector spaces, right? So all that means is like, it's the data of a diagram of vector spaces like V, W, U, whatever, with like, maps, with the appropriate maps among all of those vector spaces. With like one vector space for each vertex, one for each edge, one for each thing, and the maps just go in the appropriate way. So this is a super nice category, and in fact, so already this is an incredible result. And in fact, this category, is also known as, it's equivalent to the category of sheaves on X with singular support contained in lambda, which is equivalent to the category of sheaves. In this case, this is equivalent to sheaves of vector spaces on X, which are locally constant on each stratum.
Is X
yeah. If X is not compact, you can treat it like a Liouville sector. Well, if X is compact with boundary, you can treat it like a Liouville sector. But yeah, I'm assuming that X is a compact manifold. So let me do the example of so you can see how this calculation works, which is this example here. Let me draw it big. Okay, so what's this equivalence going to be? Well, so for each of the basically my guys are going to be my cocores and linking disks here. So for each of the big pieces in the stratification, the codimension 0 piece, I have a linking disk here. I have a cocore here, and then it's not going to be linking disks. And then for the other guys, maybe I should have drawn this in a slightly different way. Well, let me just whatever. For the other guys, what I'm going to have is guys that like cross this guy from one side to another. Okay. So this Lagrangian here is something that starts on one side and goes to the other side. So this, let me just label some of these guys. This is an edge E. This is E1, E2, P1, P2. And so associated to the edge E1 in my stratification, I have this LE1, and associated to the point P2, I have this LP2. And so you can check that kind of like hom from LE1, LE1 is just K in degree 0. So that's easy to see because, like this guy can't really do anything because here, like he wants to wrap. Here, let me just. Like I only need to look at this side of the cylinder because he obviously is never going to see the other side of the cylinder. And over here, like he wants to wrap here and this way, but like, he can only wrap a little bit before he gets stuck. So he can only sort of intersect himself at one point here. So this hom from LE1 to LE1, from himself to himself is going to be K. And for similar reasons, hom from LP2 to himself is also going to be K. So the point is that here's LP2. He looks like, oh, maybe I drew him backwards. Maybe, well, it's
true that you're taking this one as an alternative to the linking disk.
Yeah, I'm using a different set of generators here. Okay. You can sort of like
you're saying that for this description of the strategy.
For this description, I'm taking some different set of generators. sort of, which has to do with the fact that like linking disks co-represent microstalks, whereas the exit path category is about actual stalks. Yeah. And if you like think hard about what the difference between microstalks and actual stalks of a sheaf is, then you can engineer this thing here. But so the point is that like, why is hum from LP2 to itself equal to K? Well, he can't wrap very much. Again, like he tries to wrap here and he gets stuck, and he tries to wrap here and he gets stuck. So again, he's only going to like intersect himself at just this one point here. Or maybe, sorry, maybe I did this backwards. Whatever, maybe it was like, I mean, I guess maybe I did want him like this. And so the point is, well, whatever, this way he's wrapping here, but he gets stuck at the next place. Whatever, this is the next thing. He's wrapping here and he gets stuck, and he's wrapping here and he gets stuck. So the point is that whatever happens, he can't wrap very far. He's only still going to intersect himself at one point. And once again, there's some asymmetry to the wrapping, like and that's going to give you that that my like LP1 that I'm going to have, you know, hum from LP1. I'm going to have a one dimension of hum in one direction between these two guys, and a zero-dimensional hum in the other direction. And again, that has to do with the fact that like this guy is going to wrap once to see him, but he's not going to. But this guy is not going to be able to see him because he's wrapping the other direction.
So hum from LP2 to LE1 is K as well.
Yes, but hum from LE1 to LP2 is 0. And so similarly, like, you know, these are the objects that you can see that like in general, you know, in higher dimensions, it's really going to work kind of similarly to this. And so finally, you know, what I want to take away from this is that then you can combine this fact with the previous fact that I told you. You can combine this theorem with the previous theorem. So I had this previous fact, which was that if I remove a stop, I quotient by linking disks. And so now I can say, you know, let M equal T star X, and lambda.
So wait a second, sorry. So what you just explained was you gave a set of generators which are adapted to the triangulation.
Yeah.
Such that the quiver of them is the diagram of the poset.
Yeah, that the hums between them are all very simple. It's you know, it's just like there's the hums between all of them are either one-dimensional or zero-dimensional, and this poset tells you, you know, which one it is. Like it's one-dimensional if and only if it's like if the one corresponds to a, you know, a stratum, a bigger stratum. And it's zero-dimensional if it's two strata that are not related by containment. And you check that those are a set of generators because you can get them from the linking disks. And
yeah, now you're going to try to remove stops from this triangulated manifold.
Correct. Yeah. Or I'm going to say that like I'm going to start with an arbitrary lambda, which could be empty. I'm just saying let M be T star X and lambda. Sorry. Oh, you're right. I wrote something wrong here. Lambda inside that whatever boundary of M. So I'm going to let lambda be an arbitrary Legendrian in here now, which could be empty. Maybe not arbitrary. Maybe I'll demand some like vague niceness properties about lambda. And now the point is, any such lambda is going to embed inside of some lambda like this. Like, you know, I can kind of project, like assuming, again, this lambda is like, its singularities are reasonably nice, I can project it down and like stratify M by like the, you know, the singularity type of that projection or something. I'm going to embed lambda in here, and then I can remove all the stuff that's not that. Okay, so the theorem is going to be then the wrapped Fukaya category of this Liouville sector M lambda is equal to the category of sheaves on M with singular support in lambda. So the point is, we calculated that originally for lambda of this form, where lambda is a conormal to a triangulation. And now I'm saying, well, now just remove some pieces from lambda, and that's still going to be true because both of these guys satisfy this property that like removing a piece of lambda is like quotienting by the appropriate object. So the category of sheaves on X with singular support condition given by lambda, if lambda is the conormal to a stratification, especially a triangulation, is like a super nice category. So you can actually compute this directly, and then you can remove things, and you know abstractly that removing something has the same effect on both sides, removing a stop. That over here it corresponds to quotienting by a linking disk, and over here it corresponds to also a localization of this category. The like analogous localization of this category.
Okay, and in order, so this argument involves looking at the stop and comparing it with this, the stop that.
This argument involves like you starting with like this stop and then removing pieces of it until you get down to this stop. Yeah. I think. To be clear, like, I know these papers are pretty long, so I've never read them all in detail, but this is sort of what I have assumed happens in this
But
paper.
there's some sense in which the arbitrary Legendrian can be decomposed in some sense, or can be expressed as some kind of combination of these triangulations.
Yeah, the point is that like, you know, like this Legendrian like lives as like a subset of this bigger Legendrian. Like, you know, the point is that like, here, let me just, I mean, this zero-dimensional example is maybe not that enlightening, but like, if I take a bunch of stops here and a bunch of stops up here, then let me just project them down to my manifold. And then I project them down to my manifold. So these two at the bottom project to these points, these guys project to some other points, and then I just stratify my manifold by those things. And that's going to be too big because, you know, I've stratified by manifold, it's going to give me all the stuff on the bottom I didn't want because the conormals to these points coming from the top and vice versa. But then I can just remove the stops that I didn't want.
I understand, it's just that in higher dimension, this Legendrian is much more complicated than the things you get from a triangulation.
Yeah, it's more complicated, but like, it's like, I mean, if the Legendrian, let me put it this way. If the Legendrian were smooth, like then it's you know, then it's like the conormal or part of the conormal to some smooth submanifold. Namely its front projection. Like if it has a nice front projection. So like move it, if it's smooth, like wiggle it around so it has a front projection that's like a co-oriented hypersurface in M, and then like you just stratify M by like that hypersurface and the rest of it, and that's not a stratification by triangulation, but you could just, you know, stratify that thing further to get a triangulation. And you know, if it's not smooth, well, like stratify it by singularity type and then triangulate it appropriately. Again, I think this is the way it works. I'm not guaranteeing that this is how they do it, but I think this is like a, you know, a reasonable. I think this is something like what they do. They define something called a microlocal Morse theater, which I don't know what that means, but I think what it means is like they consider like structural properties of these categories as you range over all possible Lagrangians. And they find that both of these sort of satisfy the same structural property of like quotienting by linking disk does the right thing. Like, you know what removing part of a stop does. And then there's also some fact that like you can compute it like this on a big enough thing and then remove pieces. Maybe let me give an example. If lambda is the empty Legendrian, then this theorem is telling you that the wrapped Fukaya category of T star X is just equal to sheaves on M with singular support in the zero section. So this is also known as like locally constant sheaves on M or local systems on M. Sorry, on X. Sorry, M, I did this wrong. Sheaves on X. There should have been sheaves on X. I wrote it correctly over there.
The map from Lagrangian to
Yeah, so I mean, well, I mean here it's like locally constant sheaves on X. So I mean, like over here, I mean over here, the map is like if you give me like this category is generated by these objects, and these objects, each of these objects, like hom, I can calculate hom of like LP whatever, hom from LE whatever, and like these homs are computing what the stock of my sheaf is like on that stratum. And so this is a sheaf, these things are the same as sheaves on X that are locally constant on each stratum. So to know what such a sheaf is, I just need to know what's its stock along each stratum and what are all the restriction maps along strata. And so this is saying that like this is exactly that same data. So that's the way that like I can encode an object of my category in terms of a sheaf. So this, you know, this sheaf you can treat as like a combinatorial gadget as like encoding like some fact for each stratum here, but it's really like secretly encoding like the homs of these various Lagrangians with any object in this category. And so for T star M, I mean, e.g., M equals T star S1. So in that case, like after I like remove all these stops, I have only like one like object. Like after I remove all these stops, all of these objects become identified, and I just have one object remaining, and it's this cocore, and its endomorphisms. Well, it's the generator of this category, and its endomorphisms is equal to chains on the base loop space of S1, also known as pi1 of S1, also known as, I mean, sorry, like the group ring of pi1 of S1, also known as like K adjoin X, X inverse. So because like it wraps around, you know, X and X inverse down here. Maybe let me do this fully over here and explain the relation to the calculation that I just did on the place over there. So we saw that the wrapped Fukaya category of this guy, the wrapped Fukaya category of S1 with two stops, sorry, with four stops that was given by the conormals to this triangulation of the circle. We saw that this wrapped Fukaya category was equivalent to the category of representations of this quiver, which this quiver was the exit path category of my quiver. The exit path category of the quiver associated to the circle with this stratification, right? So I had 4 strata here, 2 vertices and 2 edges, and the exit paths were like the vertex can go to these 2 edges, and this vertex can go to these 2 edges. And then when I remove my stop, so remove stop, what I get is that I'm quotienting by linking disks, and it turns out that quotienting by linking disks, for basically the reason I said before, is like identifying each of these objects. Like if I quotient by the linking disk, by both of the linking disks to this stop, then if I quotient by the linking disks to, so if I quotient by the linking disk to this stop, then it identifies like this Lagrangian LP2 with this Lagrangian LE1. And similarly, because now he can wrap past, and like the difference between this and this was precisely that he was wrapped past this guy here. And so when I remove stops, then I get representations of this same quiver, where now I have required that remove stops, where I've required that all 4 of these arrows are isomorphism arrows. So yeah, so now all 4 of these guys become identified with each other, but because they're identified with each other and I had homs between all of them, these homs all become isomorphisms, and now I have a, you know, now I have a, you know, an automorphism of this object now, which is multiplication by X or X inverse. So this category is the same thing, as, you know, like representations of the quiver with one vertex and one arrow that's forced to be an isomorphism by, like, you know, contracting some of these isomorphism arrows. I mean, if I have 4 vector spaces and they're all forced to be isomorphic in a circle, that's the same as 1 vector space with an automorphism. I was trying to explain, I was teaching, like, you know, group theory for majors today, and like trying to explain why like an automorphism of a group is more exciting than an isomorphism between 2 groups. Like, it's not just that I have like isomorphisms among these, like I have them in a circle, so I actually get an automorphism of my vector space. You know, isomorphisms are good too.
Okay, so could I ask a question? So
Yeah.
let's say I have a specific question, but let me just use an example to demonstrate the question. So suppose that you're interested in the cotangent bundle of S3. Okay, so this gives a method. Let's say I triangulate my S3 and
Well, but you don't have to. I mean, you can jump right to the end here, which is that like the Fukaya category of T star S3.
But let me go. 'Cause I need the triangulation for the next step. So suppose I triangulate the S3 and I just describe.
And it doesn't have to be a triangulation. You could have chosen any, you know, like stratification of S3, and you'd still have. I mean, this theorem tells you, you know, the statement is still true for any stratification of S3.
That's fine. So what I'm interested in is, so you choose some triangulation or some stratification of this.
Sorry, and you're talking about T star S3, right? Yeah.
And that gives you a description of the wrapped Fukaya category of T star S3 in terms of inverting some localization of some
other thing. Yes.
version.
Yes.
But suppose that now I have, you know, let's say a knot in S3.
Yeah.
And I take its conormal Lagrangian.
Mm-hmm.
And I want a description of this object now.
Yeah.
Right, so if I want to describe the object in terms of the decomposition of the category that I started with, in terms of this triangulation, right? So
Right.
that I would like, for example, that the triangulation be adapted to the knot, say.
Yeah, maybe
I
so.
can chop up the knot into little pieces.
I'm
wondering
not sure if that's what you want to do, but let me say that one thing that you could try to do is, well, I mean, look what I've done here. Like in this case, like I had, okay, this guy he was not the conormal to a knot. Well, he's the conormal to a point. I don't know if a point is knotted or not in a one manifold, but whatever. He's the conormal to a point.
Yes.
And then like the triangulation was such that like I knew how to wrap the conormal to my point. Like I knew that he sort of wrapped like this. And you know, again, the wrapping is like, you know, in sheaf theory, so Chris Kuo has sort of some papers explaining how to think of wrapping purely on the sheaf theoretic side without ever going to the Fukaya category side. Basically, like geodesic flow gives you this like contact isotopy at infinity, and Guillermo Kashiwara Shapira showed you how like contact isotopy of infinity gives you this kernel, which gives you an automorphism of your category of sheaves, and then you kind of like localize at that. Basically, like the point is that like in terms of like suppose I'm looking at like locally I'm looking like down here at I'm looking at some category of sheaves on this thing, and I start with this Lagrangian here, like I said, corresponds to like the point sheaf on at a point here. And I will say like, well, how do I make this an object in my category? I'm trying to get like sheaves on, let me just say on this local piece, I'm looking at something like sheaves on R with singular support in the 0 section. But right now the skyscraper sheaf does not have singular support in the 0 section. He has singular support in the conormal to this thing here. It's not blue. No, it is blue, whatever. He has support in here. And basically, well, you kind of start to wrap this object. And like, so I've been describing the wrapping by like something your Lagrangian is doing at infinity, but like, there's also a way to say what it does to this sheaf. And basically like this skyscraper sheaf basically expands like a little bit to like the push forward of like the constant sheaf on this sort of like interval, which is what you get by kind of like doing the geodesic flow in both directions from this guy. And this interval kind of expands and expands. And if you were doing it on here, then what you get is that like this point sheaf expands and expands until he hits the other strata in here. And so you get that like this object here, which was like the conormal to this point, becomes in sheaf theoretic language the like push forward of the constant sheaf on this like interval here. So
So the question that I had is the following. So I'm asking, you're telling me how to build the category out of pieces via localization.
yeah.
What if I have an object in the endpoint category? Can I take that object and decompose it into pieces as well? In other words, if I have a general object and if I want to express it in terms of this basis, is there a geometric way?
Well, but I don't know if, I mean, I don't know if off the top of my head I have a good answer to your question. I mean, one thing I can say is that you could, for instance, like, I mean, I would try and figure out, I would find some like maybe generators of my category that are well adapted to this decomposition of the category that you like, and see if I can figure out how to express my object in terms of those generators. So like, again, when I wrap this object here, well, I guess this object is one of my generators because he's a co-core, but like when I wrap this object, ultimately, like he starts to look something more like over here, he's wrapping this way, and over here, he's wrapping this way. So he starts to look something like this, right? This is the singular support. This little picture here is the singular support of the sheaf that's like the push forward of the constant sheaf on this interval here. And then, I can say like, oh, well, I understand this in terms of, I don't know, whatever. Like I'm saying that maybe if you wrote your object as like an iterated mapping cone of some like linking disks or some other things.
That's right. So imagine you took an example of graph that began at some point on the top and circled around several times and exited the bottom.
Yeah.
That object is not contained in any one of your strata.
Yes.
It spans multiple strata.
Yes.
So what are you supposed to do to analyze that object?
Yeah, I mean, well,
To kind of.
Yeah, I might try and write it again. I might try and write it as a cone of multiple kind of linking disks. I mean, basically, that's what it means to describe it as an object of your category algebraically. Like when if I had some object here. Well, what I'm saying is that like the way I proved this isomorphism is that I found a really nice set of generators for this category, and I computed their HOMs. And now, how do I understand a general object in this category? I take its HOM with all of those generators. And taking its HOM with all of those generators is precisely a way of saying that like, okay, I've expressed my object, like whenever you say that like, this is just some general algebraic statement here. If I have like G is a generator of a category C, then by some sort of Barbeck type nonsense or monadicity or something, C is like a category of modules in nice cases over the endomorphisms of the generator. What am I saying when I make a statement like this? I'm saying that when I take an object of C, right, and the or maybe G op or something, I don't know, endomorphism G op, I'm not sure. If I take an object in C, this equivalence here is like given an object in here, I look at like HOM from G to C, and this thing has an action of this algebra on it. So it's a module over this thing. And so the point is that like this space here is like telling me this with its action of endomorphism of G is sort of like telling me how to build up C as a let me put it this way. I've reduced myself to algebra here. I've reduced myself to like I'm looking at the category of modules over a ring. If you're looking at the category of R modules and someone gives you an R module M, the best thing to do is to take a free resolution or a projective resolution or something of it. And that tells you how to build up M in terms of R and maps between R. And so what I'm saying is that like, if you understand the object of this category in terms of some nice set of generators, that's telling you how to build up your object in terms of those generators. And then you can kind of try and do lots of things with that. Then you're just like doing pure algebra at some point. That's my like, vague structural answer. I'm sorry I don't have a, more direct answer, but
Is that if I have a general Lagrangian, then what you're telling me is, if you know a generating set for your category, you can just, and if you knew how to compute on from that generating set to this object, then
yes,
you could figure out the module, algebraic module that this
Yes.
Lagrangian corresponds to.
yes,
But I want to make computations in the stopped category, because that's the only category I can actually compute it.
yes, but I was talking about generators for the stopped category.
Well, okay, but if I have a general object which is not in the stopped category,
No, what do you mean it's not in the stock? Any object is in whatever category, like,
I see.
again, the only thing I required about my Lagrangians is that they be disjoint from the stops.
So I'm supposed to compute palms in the stopped category to understand the relationship between the generators of the stopped category and my general object. And that will give us enough information to.
That's what I would recommend. I would say that, like, in this category, I told you a set of generators, namely this guy, this guy, this guy, etc. And like those guys completely determined what your Lagrangian was doing, like what it could be, what its possible behavior was in the stopped category. And then once you know that, then you're in a setting of pure algebra. You're in a setting of modular representations of some quiver, just a poset quiver in this case. So. Yeah.
This may be irrelevant, but like, what if we run the inversely Fukaya? So that's like when studying the limit, like, and see what kind of components does it have.
Yeah, I mean, that's kind of, in some sense, that's kind of what's underlying this isomorphism here between like the wrapped Fukaya category and sheaves. That's why kind of like a sheaf, like there's something weird here where in my wrapped Fukaya category, I was drawing like these curvy kind of Lagrangians, but a sheaf always has singular support that's conical, right? I said that like if I took my actual sheaf, then like it had singular support that looked like this. So you can imagine that like this thing here was like a limit of like taking some, Lagrangian like this LP2 and then like, doing some Liouville flow and wrapping, like combination of like the wrapping with the like reverse Liouville flow is going to force me to give me something conical kind of. Well, no, there is. Once you know the theorem, then you can just forget about this. Now we prove this theorem. Like the theorem is now that like the Fukaya category is equivalent to a category of constructible sheaves.
There's no direct way to see what's.
Well, I would say that okay, so there's this, no, there is, so now there's this, okay, this would be another, I gave already a 2-hour talk at Nick Rosenblum's seminar about this question. There's this paper of David Nadler and Vivek Shenda about, roughly speaking, what you'd like to do is you'd like to take your Lagrangian and apply, as we said, apply like reverse Liouville flow to it. And then the reverse Liouville flow is going to like force it, like kind of like suck it into the skeleton of your manifold, basically. If it were just a cotangent bundle, then X or, the point is like you want to turn your Lagrangian into something that's, there's more general Weinstein manifolds than just cotangent bundles. Like, you might have had something that was no longer a cotangent bundle. Its skeleton was like, something like this, whatever. And then, and you had some like, Lagrangian in here, and you want to know like, what does that correspond to? Well, just do reverse Liouville flow, and that'll kind of suck it in. And the idea is like, okay, how does that actually give you a functor from like my Lagrangian? Okay, my Lagrangian, let me say, it's really my Lagrangian with a local system. So like what your question is asking is like, what's the name of the functor given some Lagrangian L like this? What's the name of the functor from like local systems on L to constructible sheaves, or really microlocal sheaves on the skeleton? And the idea is that like there should be something like I have like a family of Lagrangians LT, where T is like the Liouville flow sucking you in, and then you want some version of like nearby cycles. This goes under the name of kind of like nearby cycles. If I have if I have like a manifold X mapping to like R greater than or equal to 0, there's some way of like taking a sheaf on X. So inside of R greater than or equal to 0, I have R strictly greater than 0. Let me call this X strictly greater than 0. And then I also have 0. I have X0, my central fiber, mapping in here. So let me call this J, this inclusion, and I, this inclusion. And so the idea is that if you have a sheaf on X, you can if you can pull it back to X greater than 0, then you can push it forward, then you can pull it back to X0. So I have some like family of things. I have this family of like LT, where as T goes to 0, LT is like going into the skeleton by the reverse Liouville flow. And I can think of this as like some family. I have like family of like sheaves whose like singular support is like varying. And I want to know how is the behavior of my sheaf like change as it goes to this singular thing here. Sorry, I'm being vague. There are sort of like some tools that you have to deal with this. And like we are getting to a point where like everything can be done purely in terms of sheaf theory in this Weinstein setting. But maybe
Is it a good place to stop?
Maybe this is a good place to stop. I could say one more thing, or we could just stop right here. The one more thing, okay, I'm already over time. Well, okay, I'll say one last, I'll just give you a general strategy for computing the wrapped Fukaya category outside of a cotangent bundle, since this was just about cotangent bundles. So I would like to say, some people might be interested in things in life that are not cotangent bundles. So I'll just say strategy for computing the wrapped Fukaya category of M, where M is a Liouville manifold, Weinstein manifold that's not a cotangent bundle. So steps 2 and 3 we've already talked about, but I'll say step 1 is this is just reiterating what I've already said, but find a skeleton L using Morse theory. 2 is like decompose L as a union of some Li. These are skeleta of simpler Liouville sectors. And then 3 is glued together. Maybe these are skeleta of simpler sectors Mi, and 3 is glued together the wrapped Fukaya categories of the Mi. So I've already said these ingredients. I just wanted to finish by packaging them together and saying that oftentimes, like even 1, which I haven't really spent much time on, is already kind of can be a very difficult thing. I mean, like, yeah, for a punctured Riemann surface, like it's just finding a ribbon graph, which whatever, you can just do that by hand. Like if I have a higher dimensional manifold, I really need to write down a Morse function that's adapted to the Liouville flow, and then do Morse theory to like find a nice skeleton. Sorry, yeah. Oh. So okay, I think now is a good point to end.
Okay, thank you so much.